Here, then so please, when you want, just a comment. This, and given this point, it seems that yes, you may not ask questions. Talk, so we do after when you
Hello, can you hear me? I'm trying to share the screen. Let's suppose you have a copy of my slides. Share screen. Is my screen coming through? I don't know. It's coming through. Okay. Okay. Can you see it full screen now? All good. I've closed everything here now. Is it all okay? Oh, that's good. Yeah. Okay. Sorry. Okay. Hello, everybody. It's a pleasure to be invited to give a talk at Beyond I.I.D. I'm really excited. I'm also a bit sad that I cannot be there physically, so this is the next best thing. And I thank the organizers for inviting me. In fact, they did so at very short notice. And thank you to all for taking the time to listen to a ghostly video talk. Okay, so the title of my talk is Unions, Intersections, and a One-Shot Quantum Joint Typicality Lemma. It is based on these two papers which are uploaded on the archive. The talk will mainly focus on the first paper, which contains the technical result, the one in blue. And the second paper is on applications of this joint typicality lemma to some problems in network information theory. Step ahead. Right, okay, good. Yeah, so let's start with some motivation for this problem. The motivation is a one-shot simultaneous decoder for the multiple access channel. Okay, so I suppose everybody here knows what's the multiple access channel. So it's a channel with two senders. We'll call them M and N, and they're sending classical messages, little m, little n. They encode the classical message M into a quantum state rho m, sigma n. The encodings are done independently as exemplified by the tensor product. Then the quantum states are fed as input to the channel C. The output is a quantum state, which I'm calling tau. The subscript Mn indicates the dependence on the classical messages M and N. And then the receiver applies a decoding superoperator and gets his guess M hat, N hat of what was sent. And we want that the probability that the guess is not equal to what was exactly sent should be small. Okay, and we are choosing the message pair Mn uniformly. Okay. Now we want to give inner bound. So these are achievable rates. So it's a rate pair. R1 is the rate from sender 1 to the receiver. R2 is the rate from sender 2 to the receiver. So to define an inner bound, we need to define a CQ, a classical quantum state tau. It's classical on registers M and N and quantum on the register Z. To define that, we will throw in independent probability distributions P and Q on the sets M, N. Okay, and the output of the channel Z is of course determined by by the message pair Mn, so it's tau Mn. So the state, I suppose, is clear to everybody. Now this is the state tau, and the inner bound that I would like to prove is given by this. So many of you have probably seen this kind of inner bound. So let me remind you. So in the I.I.D case, where the same channel is applied independently n times, this inner bound, in fact, this is the optimal result rate region. So this inner bound was shown to be achievable long ago in 2001 by Andreas Winter. And since in the I.I.D case I'll emphasize by multiplying by n, so the achievable rates rate pair R1 R2 has to satisfy this inequality. Okay. And what you see here for the one shot is the natural one shot analog of that. There is no n here, of course, because we are using the channel only once. The Shannon mutual information I is replaced by the hypothesis testing mutual information defined analogously. We'll define it formally in a moment. So the hypothesis testing relative entropy is the one defined by Wang and Renner. We'll define it formally in a moment. So this is the desired one-shot inner bound. Now, Winter proved the I.I.D inner bound long time ago, but why does the proof not generalize to the one-shot case? So the problem arises because of the issue of simultaneous decoders versus successive cancellation decoders. So this is the I.I.D inner bound proved by Winter. Note that I've ignored the delta for ease of notation. So this inner bound is this pentagonal rate region, as you can see. And the successive cancellation strategy focuses on decoding two special points. The blue point here that I'm calling A, and the red point here that I'm calling B. Okay. So these are the points where the rate pairs are given as shown in the diagram. So let's concentrate on the point A. How do I achieve this rate pair? So this can be achieved by first decoding n, okay, from Z. So I'll decode n from Z as if there's a point-to-point channel from sender n to the receiver Z. The other sender's work is treated as noise. So I get the mutual information I of nz, okay? And then what the receiver does is you uses the decoded n together with the output z that he already has to decode the other message n, okay? So now the rate that one can hope to achieve is the mutual information between m and nz. So nz is already available at the receiver's end by this time, okay? So this is the point A. And there's a similar strategy for the point B where one first decodes the message M, assuming it's a point-to-point channel, uses that as side information to decode the message M. Okay. Now note that once I get these 2 points, now how do I get the other points? For example, how do I get the yellow point? The yellow point is a convex combination of the points A and B. And the rate pair corresponding to the yellow point can be achieved by a strategy called time sharing. So time sharing achieves this point by transmitting at rate pair A for alpha n channel users and at rate pair B for 1 minus alpha times n channel users. Okay. So overall we get the rate alpha A plus 1 minus alpha B. So time sharing combined with successive cancellation gives the entire rate region for the I.I.D case. So this works in classical I.I.D, this works in quantum I.I.D. Okay. But here is the problem when it comes to one shot. So time sharing makes no sense for one shot. So successive cancellation, we can do it for one shot, but we'll only get achievability for the point A, for the point B. We'll not get the full rate region. Okay. So here we crucially need what is called a simultaneous decoder. So the simultaneous decoder can decode the yellow point directly. Okay. So let's see as a warm-up how one can get a one-shot simultaneous decoder for the classical multiple access channel. So it's the same as before. Okay. I'm going to use quantum notation tau mnz even for classical probability distribution so that I have consistency with the later quantum work. Okay. So let's define the hypothesis testing mutual information between m and nz, for example. So for that I have to define some function fm, which I'll call a classical POVM, keeping in mind the quantum POVM that will appear later. So classical POVM is nothing but a classical hypothesis test. I mean, that's the more popular jargon classically, but I like to call it a classical POVM. So a classical POVM or hypothesis test on the alphabet m and z is a function which for every sample point m and z chooses to accept it with probability f m and z. Okay? So think of it as tossing a coin. whether to accept the sample point M and Z or not. For different sample points, I have different probability of heads for the coin. So in other words, I have a function f from the sample point to 0, 1. This is a classical POV. And to define the hypothesis testing mutual information, I'll maximize over all classical POVMs that accept the correct joint state with probability 1 minus epsilon. And I want to minimize the probability of accepting a negative state. So the negative state for this definition is the tensor product of marginals on M and the marginal on NZ. Okay, so I want to minimize it, which is as good as you take log and negative and maximize it. So one can define the other hypothesis testing mutual informations accordingly. Okay, so let the optimizing classical POVMs for these two definitions be F sub n and F sub n. So in general, the optimizing classical POVMs for these three definitions are different. Okay, so let's keep that in mind as we go ahead. Okay, so we want to find a simultaneous decoder. So we have this probability distribution, the correct joint probability distribution tau on M and Z. So we'll use a sequential decoding strategy, which is very simple. So suppose M prime, N prime is transmitted and some symbol Z is received. Okay. So the sequential decoder cycles through all Mn in lexicographic order. Okay. Lexicographic order is not important, just some definite order. So the strategy is accept the current candidate Mn with probability F, M and Z. Remember, Z is what was actually output. So if this accept really works, then stop and declare the guess M hat, N hat to be the current Mn. If this accept does not work, which is with probability 1 minus F, okay, then continue, go to the next candidate. And keep going. If at the end you have never accepted, then just declare error or something. Now, the question is, what is the F that I'm going to use in this sequential decoding strategy? So F is the classical POVM or the hypothesis test got by intersecting Fm, Fn, Fmn. So by intersecting, I mean for every sample point M and Z, the intersection POVM will assign the minimum probability of acceptance. Okay, so there are three prescriptions for probability of accepting the sample points corresponding to three tests. Take the minimum probability. Okay, so let's see why this works. Okay, so this is the importance of intersection. This is what was known as joint typicality in classical information theory literature. Okay, so joint typicality essentially means it's the intersection of typical sets. We don't have typical sets, we're in the one-shot case, so we have intersection of classical POVs. Okay, so we have the correct probability distribution tau as defined naturally. And let us say M prime, N prime was transmitted and some symbol Z was received. So let's look at the case 0. So the current candidate that we're considering Mn is same as M prime, N prime. But somehow we are foolish enough not to accept it. So let's see what is the probability of not accepting this. So now, of course, since the like Mn is M prime, N prime, the received symbol Z is distributed according to the correct probability distribution, M prime, distribution on Z, condition on M prime, N prime. So now if I average over all messages, M prime, N prime, the probability of not accepting is given by this. So remember, F was the minimum, the intersection POVM. I will do a trivial upper bound of 1 minus the minimum by sum of 1 minus Fm, 1 minus Fn, and so on. And then this gives me 3 epsilon. Okay, so this is well and good. So the so-called type 1 error or case 0, the probability of not accepting at the correct guess is less than 3 epsilon. Now what about the wrong guesses? So M prime, N prime is transmitted, recall that. But now my current candidate that I'm checking is M double prime, N prime. That means the candidate agrees at coordinate N prime but disagrees at the coordinate M. Okay. So now the Z is distributed according to actually tau M prime, N prime. Sorry about that. But anyway, this equation is correct. So averaged over the messages, the probability of accepting. So remember, this is a wrong case. I should not accept it. So the probability that I nevertheless accept is given by the intersection POVM applied on the tensor product of marginals. So why does the marginal M come out? Remember, my current guess M disagrees with the actual message M prime. Okay, so that's why it stands out as tensor product. But because of the definition of the intersection P of M is the minimum, I can upper bound it by Fm. And remember, Fm is the optimizing P of M for this definition. So I get this. Okay. And similarly, the same proof will work for case N. So this is when I disagree on I disagree for the sender 2 but agree with sender 1. And case Mn is when my current guess disagrees with both. Okay. So the proofs go similarly. So let's tie it all together. Okay, so the probability of error is less than 3 epsilon, that is case 0. Okay, so this is when I do not accept the correct the correct pair. Then case M, I get this. So it's just union bound multiplies by 2 to the R1. Case N, case Mn. And overall, the way R1, R2 are chosen, and we have the bound on R1 plus R2 also. So this becomes less than 6 epsilon. Okay, so bingo, I've got a simultaneous one-shot decoder for the classical bank. Okay, so let me pause. So I hope everybody understands up to this point. Yeah. So should I go ahead? Okay. Yeah. So let's try to extend these ideas for the quantum multiple access channel. So we have the same kind of definition of tau. Now it's a CQ state defined analogously. So remember, Mn is classical, but now the state of Z condition on Mn is a quantum state. We have the analogous definition of the hypothesis testing mutual information. So now there is a maximization over quantum POVMs, POVM elements pi m. Okay, so pi m is a POVM element on M and Z, but because it's a CQ state, I can assume that the POVM also respects the CQ structure. So what does the POVM do? It just looks at what is there in the classical registers Mn, and condition on that applies a certain POVM pi sub little m, okay, on the system side. And again, I want this quantum POVM to accept the correct joint state with probability 1 minus epsilon. And I want it to accept the negative hypothesis, which is the tensor product of marginals, with as low probability as possible. Okay? So this is the expression for that. And similarly, one can define the hypothesis testing mutual information for N with MZ and Mn with Z as before. But now I'll get different optimizing POVMs in general. So there are 3 such quantities and 3 such optimizing POVMs, pi m, pi n, and pi l. Okay, as before. Okay. So let's try the same thing. Let's try the sequential decoding strategy. Okay, remember n prime is transmitted. I'll cycle through all Mn in lexicographic order. And the strategy is accept the current guess Mn with probability, this natural expression. So the state at the output is tau condition on M prime N prime, which was exactly which was the thing that was exactly transmitted. But now my guess in the decoding algorithm is some Mn, which may or may not be the same. And the question is, what is the probability that the test for Mn accepts tau M prime N prime? Anyway, so if I happen to accept stop and declare my guess, M hat N hat is Mn, if not, continue to the next candidate. Now, this sequential decoder can be analyzed with a tool called the non-commutative union bound, and we get roughly the same performance as in the classical case. So that's not an issue. Okay, so the only question is, what is this quantum POVM pi z? So I would like to say it is got by intersecting the three quantum POVMs for the case M, case N, and the case Mn. But wait a minute, what is intersection? Okay. So what is intersection of projectors? So for later convenience, the rest of proof will be rather geometric. So we'll replace POVM by orthogonal projection using Gelfand-Naimark. Okay, so instead of intersecting POVMs, we'll try to intersect orthogonal projectors. So let's see. What is the intersection of projectors pi 1 and pi 2? So here is the first attempt. So pi 1 projects to V1, pi 2 projects to V2. And my intersection is just the intersection of the spaces. Okay, V is V1 intersection V2. So this seems to be good. It indeed controls the error in case M, case N, and case Mn. Remember, case M is when my candidate guess agrees for sender 2 for the alphabet N but disagrees on the alphabet M. Okay, so on and so forth. So the intersection controls the error as before for these three cases. But the problem comes in case 0. Unfortunately, V1 and V2 do not, these two spaces, these two projectors do not commute in general. So in general, I'll actually see that the intersection of these two spaces is a 0 space. So case 0 will give probability of error less than 1. Okay, more formally, so the probability of error in case 0 is given by this quantity. So remember, Mn is transmitted and I'm checking for the same Mn. So one can expand it out. And now what is pi? Pi is the intersection of the three POVMs, intersection of three spaces. But that's a 0 space, so I'll get 1 minus 0 equal to 1. So this fails in case 0. Okay, let's try another idea. So here is my second attempt. So my intersection projector is a product, okay, so of projectors of M, N, Mn in some order. Okay. So this is not so bad, or so it seems. So this indeed controls the error in case 0. Case 0 is when I'm checking for Mn and Mn was indeed transmitted. So this controls the error in case 0. It's easy to prove. One can prove it by gentle measurement lemma of Winter, or one can again prove it by non-commutative union bound, no problem. But the problem comes with the other cases. So unfortunately, the projectors pi m, pi n, and pi mn do not commute in general. So we cannot control all the three cases simultaneously. So the way I've defined it, it turns out that one can control case m out here. Note that pi m is at the outermost layer. Pi m is at the outermost layer here. So I can control the error in case m for this definition, but not in case n. Let's see why. So case n is mn prime is sent, but I'm checking for mn where n is different from n prime. So one can write down the expressions, and what we get tensor product of marginals, but because n prime is different from n, this tau n comes out like this. And let me write the expression for pi, which is this product. But remember, the projector that is hitting my tensor product of marginals, my negative hypothesis state, is pi m. And there's no guarantee how pi m behaves on this state. I know how pi n behaves on this state, but I have no idea how pi m behaves on this. So what is this? No idea. Okay, so we fail again. Okay, so let's still try. So we are still trying to come up with intersection projectors. So this is how we'll go ahead. Let us go back to attempt 1. Remember, attempt 1 was the intersection of spaces, indeed the geometric intersection of vector spaces. But instead of intersection of spaces, I will try a different tactic. So I'll take the complement of V1. Remember, V1 is the projector onto the good space. Okay. But I'll take the complement of V1, I'll take the complement of V2, take the span indicated by plus, and then take the complement again. So I'll call it attempt 1 prime. But wait a minute, that is the same as V1 intersection V2, so it shouldn't give anything different, right? So recall what was the problem with V1 intersection V2? In general, V1 intersection V2 will be the 0 space. So that manifests itself as the span of their complements is the entire Hilbert space H. So what does it give? So what do I know? If I look at the true joint state tau on M and Z, so remember V1 is the good state which will accept, V1 is the good projector which will accept tau with probability 1 minus epsilon. So V1 complement will accept tau with probability at most epsilon. Okay, so this is what is captured. So the probability that V1 complement accepts tau is small, less than epsilon. V2 complement also accepts tau with probability less than epsilon. But yet, this seems to suggest that the span accepts tau with probability 1. Is this possible? So it turns out it's actually impossible if epsilon is 0. Okay, so if epsilon is 0, then I will get a 0 here instead of 1. But it's very much possible otherwise. You take any small non-zero epsilon, it's very much possible. And here is why. It is in fact even possible in two-dimensional space. So let's say V1 complement is the projector onto this one-dimensional space. V2 complement is the projector onto this one-dimensional space. And here is the true state tau. In fact, V1 complement accepts tau with probability 0. It's perfectly orthogonal. V2 complement accepts tau with probability at most epsilon, small non-zero epsilon. But the span of V1 and V2 is the entire plane of the screen. Okay, so it accepts tau with probability 1. Okay. So there's nothing we can do about it. But we'll pause and think, what is the culprit? What is the geometric culprit behind this? So I mean, why in the classical setting it was not a problem? So the culprit, as it turns out, with some thought, is the small non-zero angles between the spaces V1 complement and V2 complement. So small and non-zero. This is the culprit. So let's look at an attempt. We are looking at span of V1 complement and V2 complement. Okay. And the culprit is a small non-zero angle. So if the angle was indeed 0, if tau was orthogonal to both V1 complement and V2 complement, it's orthogonal to the span. So angle of 0 is manageable. Or angle of nearly pi by 2. So nearly pi by 2 would be V2 complement is somewhere here. V2 complement is almost orthogonal to V1 complement. So this is like the classical case. So this, so the span is like the union of sets. So V1 complement is one set, V2 complement is a distinct set. So it's just union of sets. And classically, if you think of them as sets, remember, two sets can have elements in common, so the angle is 0 for those elements, or the remaining elements are distinct, which means the pairwise angles are pi by 2, exactly pi by 2. So more generally, angle of exactly 0 or nearly pi by 2 is manageable. Okay. This pathological behavior will not manifest itself. But in general, we cannot hope that the angles between two spaces V1 complement and V2 complement, about which we have very little idea, we cannot hope that the angles are either 0 or nearly pi by 2. So what do we do? So here's the solution. The solution is we'll artificially increase angles between subspaces by tilting them in orthogonal directions. So this is new idea number 1, that is tilting. So tilting will require us to enlarge the Hilbert space. So we were working in the original Hilbert space H, but let's say we have two subspaces out here, V1 complement, V2 complement. So to tilt them in orthogonal directions, we have to introduce two orthogonal spaces, H1 and H2. So H1 is isomorphic to H otherwise, H2 is isomorphic to H otherwise, but all these are orthogonal to each other. So we'll work in the enlarged Hilbert space H tilde. And we have the isometry T1 that takes me from H to H1, T2 takes me from H to H2. Okay, and what do I mean by tilting along direction 1 by a small parameter alpha? It is this candidate, which you can see geometrically. So this is the original V1 complement living in H. I tilt it along orthogonal direction Y slightly. Okay, so think of alpha as a small quantity. So this is tilting along direction 1. So in this case, it's tilting along the y-axis in the plane of the screen. And tilting along direction 2, so I could not draw it properly. This is tilted along the z-axis, which is coming out of the screen. Okay. So V2 is tilted by alpha, but not along the y direction, but in an orthogonal direction, let's say the z direction. So it's tilted into the Hilbert space H2. So if I have three such vector spaces, I'll have to introduce H1, H2, H3, and I'll tilt them along three orthogonal directions. Okay. So this actually does a beautiful thing. So I'll call it the vanilla tilted span. Tilted span means I'll first tilt and then take the span. Okay. So let's take a vector V in the original Hilbert space. So V here is this state tau. Okay. Now let us say the probability of projecting V onto pi I is small, less than epsilon for all the I. So I have pi 1, pi 2, pi 3, whole host of them. Okay. Now, what I'll do is instead of trying to project onto the span of pi 1, pi 2, pi 3, and so on, I will first tilt pi I. So I'll tilt pi I to pi prime I, which is the alpha tilt of pi I in the ith direction. Okay, remember the different directions are orthogonal. And now, pi prime is the span of the tilted pi i's. Okay, so the span lives in the enlarged Hilbert space H tilde. Then we have this very nice result. So, so I can say that the probability of the state V projecting onto the tilted span pi prime. So it's lower bounded by 1 minus alpha times epsilon. This is easy to prove from the definition of tilting. But amazingly, it's upper bounded by something which very much looks like a union bound. Okay, so there's just this price of 1 minus alpha by alpha. So remember, if alpha is 0, that means I don't tilt at all. Then there is no upper bound. And this upper bound is infinity. Okay, and if alpha is and if alpha is 1, then then the tilts are all in orthogonal spaces. So remember, V is in the old Hilbert space H, but pi prime 1, pi prime 2, pi prime 3 are all in H1, H2, H3, which is orthogonal to H. So then the upper bound becomes 0. Okay. But the interesting case is when we have a small non-zero alpha and we have a very nice union bound. So this gives a very general way to do union of projectors. So already this result improves the result of Anshu, Jain and Warsi for the inner bounds for the compound channel, and you should have more applications in quantum information as well as quantum computational complexity. So I expect this to have a lot more applications eventually. Okay, so we have a way to do a union as promised in the title of the talk, okay. So which is the vanilla tilted span. Let's see if this helps me. So unfortunately, tilting alone does not give intersection. Okay. So I have the tilted span, satisfies the union bound. And remember now, what is my prescription of intersection? First take V1 complement, take V2 complement, take the tilted span. So this union means the tilted span. And now take the complement of this. So this V does not live in the old Hilbert space, it lives in the enlarged Hilbert space H tilde. So this does something good. Remember, in the original intersection argument, case 0 was the one that went for a toss. The other cases were under control. But here case 0 comes under control. So case 0 is when Mn is sent and I'm checking for the same Mn. So you can put that expression in, okay, and now we have the tilted span pi prime. We have the union bound for that, okay, and we'll get a quantity like this. So not 3 epsilon as in the classical case, but a little larger. You can take, for example, alpha to be half and get 3 epsilon out here. Okay, so what is pi prime? Pi prime is the so-called union of the tilted span. So recall, it is the complement in the enlarged Hilbert space H tilde of the tilted span of complements of the 3 POVMs, pi n, and pi mn. So I'm taking the complements of these POVMs in H. So these are the bad subspace of H. Then tilt them. Okay, but if I tilt them, I go out of H into H tilde, and then take the complement of the tilted span in H tilde. That is pi prime. Okay. For that we have this union bound. So very good. Case 0 is under control. But unfortunately, now case M, case N, and case Mn go for a toss. So it's like a balloon. You try to squeeze at one end and something else comes out. So let's see why case M goes for a toss. So we write the equation for case M. Remember, case M is M prime N is sent, but I'm checking for Mn. So my guess agrees in the N coordinate, but disagrees in the M coordinate. So now I have pi prime, but I'm checking against, this should be tau M tensor tau NZ, sorry. So M is the wrong guess, so that comes out as tensor product. Okay. So no problem, but so I can use the other side of my tilted span union bound. So I can use this, okay, but now I get this expression. So the problem here is this alpha. So if the alpha were 0, then I would have actually got 2 to the minus I, exactly the quantity that I want. But of course I cannot take alpha equal to 0. If I take alpha equal to 0, case 0 will go for a toss. Remember, alpha is in the denominator out here. Okay. But if I take any non-zero alpha, fixed non-zero alpha, then this quantity is no longer small. So I failed again. So this, so to handle this, we need new idea number 2. So new idea number 2 is smoothing and augmenting. So what is smoothing? So I will tilt, okay, I'll tilt the state tau. Okay, suppose Mn is transmitted, I'll tilt the state tau, not along one particular direction, but simultaneously along several orthogonal directions. So in our case, we will tilt along 3 orthogonal directions, and we'll call them Mn, M, and N. Just to remember what this means information theory. So they're just three orthogonal directions that I tilt them along. So what do I mean by tilting simultaneously along orthogonal directions? So I take a linear combination of the original state vector in the Hilbert space H together with a little bit of a component along this space, along this space and this space. Okay. See, one has to carefully choose the coefficients for tilting along these three spaces. The details are in the paper. Okay. But the point is, to do smoothing, I simultaneously tilt along several orthogonal directions. Now, what does this buy me? So suppose I trace out n from here. Okay, I average out n, which will be required when I analyze case n. Case n is when my guess disagrees for n but agrees for n. Then I have to look at this state for my error analysis, which is defined by averaging out n. So the point is, if I tilt this tau along three orthogonal directions and I then average out n, something amazing happens. So it turns out this is tilted mostly along n, as averaging over n smooths out the other directions. The other directions n and mn are sort of sensitive to the classical random variable n out here, and they get smoothed out by this average. Okay, so this requires some work to prove, and mostly means that the state tau condition on m is a convex combination of two quantum states. The first state is tilted only along direction m, and the second state is the so-called error part, the junk. Okay, that all bets are off. That's some state that lives in the extended Hilbert space H, but that has small shattered L infinity now. So this is the catch. Okay, but to make this work, I mean, to really make this L infinity norm small, one requires that the distribution Qn has high min entropy. Okay, some of the min entropy of Qn translates into the L infinity norm. Maybe not hard to believe. Okay. But we have no control over Qn. I mean, how can you ensure that it has high min entropy? So this requires the second part of the idea, which is augmentation. So let us tensor in completely mixed ancilla. So it's a completely mixed state over another ancilla register n. So I'll tensor in this completely mixed ancilla for m as well as for n independently, and I have to take L large enough to provide the required min entropy. So now if I do so you first bring in the augmentation, and then if I do the smoothing, so this will ensure that tau m is tilted mostly along m, tau n, okay, when I've averaged out the register m now, so tau n is tilted mostly along n, and tau z, when I've averaged out both m and n, is mostly untilted. Okay, so this is the amazing thing. So I mean, there's a jump part, but that is very small. And I'm mostly tilted in the so-called correct direction. And turns out this idea works. So here is the intersection definition that actually works. So recall we tilt tau mn along simultaneously along these three directions. Now the tilted state that I'm going to call tau prime mn is close to the original state tensored with the augmentation ancillas for m and n. So I have two augmentation ancillas out here, but it's close. So let's define this quantity. So what is pi tilde m? So recall we had the classical recall we had the POVM element pi m for the case m, for the mutual information quantity for the case m. Okay. So we have the projector pi m, let us say. So this lives in H. So we'll first take its complement in H. So that is the bad set. Then we'll tilt it along direction m. Okay, and then we'll take the complement of this tilted space in the extended Hilbert space H tilde. Okay, so start off with the good old POVM or the good old projector. Take its complement in the good old space H, tilt it along direction m. So now I'm entering the larger Hilbert space H tilde, and now take the complement in the larger Hilbert space H. So that is pi tilde m. So similarly, I can define pi tilde n and pi tilde mn. Okay. Now my intersection that actually works, pi hat, is the intersection of these three spaces, just the intersection of subspaces. And this pi hat works as a good intersection of projectors. So let's see why. Let us see that case m, n and mn are under control now. So I'll just show the proof for case m. The others are very similar. So case m is when my guess agrees for n but disagrees for m. So remember, like, I'm working with a tilted state tau prime. So it disagrees on m, so tau prime m comes out as tensor product, and I'm hitting it with my intersection P of m pi hat. Okay, so this is the error probability for case m. Okay, so I've sneaked in this pi tilde m. Remember, pi hat is the intersection of all of these. Okay, so this space pi tilde m is a larger space. It's a super space of pi hat. Okay, so I can sneak it in here. There is a equality. Okay. Now, after I sneak it in, I'm going to remove this outermost. I mean, these are after all projectors. They will not increase my probability. So I remove that, and I'm just working with this. Now here is the key thing. Okay, so remember, tau prime is mostly tilted along direction m, and tau prime m, and tau prime nz, okay, is basically tilted along direction n. Okay, so so there is of course a tiny junk part. So remember, this is a convex combination of the ideal state, okay, tilted along the correct directions, and the junk. The junk is very small, so that's only going to give a small quantity. Let's look at the modal state. So this is tilted along direction m. This is tilted along direction n. So and this projector pi tilde m is also tilted along the same direction, m out here and n out here, m tensor n. Note that m tensor n is not the same as the direction mn. Okay. So this trace, this probability is exactly the same as if I worked in the original space. Okay. So because the state is tilted along a direction m comma n, this pi tilde is also tilted in the same direction m comma n. So because of isometry, the same thing is going on as if in the old Hilbert space. So in the old Hilbert space, I have tau m tensor tau nz, and I have pi m. This is exactly the quantity that arises in the mutual information quantity, and I get this. So this brings case m under control. Similarly, case n, case mn. Okay. What about case 0? So case 0 is when mn is set and I'm checking for the same mn. One cannot apply directly the vanilla tilted span theorem, because now recall I'm working with tilted state tau prime. Okay, and then in the analysis I will look at states like tau m tensor tau n. So there are various states that appear in the various equations in the analysis. So different states are tilted along different directions. So tau m tensor tau nz is tilted along pure m comma n. So there's pure m coming in, pure n coming in, and the linear combination of m, n, and mn. I mean, this linear combination is the tilt of the original state tau prime. But if I look at tensor products of marginals, they're tilted along different directions. Some are tilted along pure m comma n, pure n comma m, and so on. So I cannot directly apply the tilted span theorem. But nevertheless, we can extend the tilted span theorem to something called matrix tilted span. Okay. So instead of tilts along orthogonal directions, we have to handle tilts along non-orthogonal directions. So the tilting parameters now form a matrix. So that's why matrix tilted span. So, but nevertheless, one can prove a theorem for matrix tilted span and finish the proof for case 0. So I'll not get 3 epsilon. I mean, the parameters are not so nice, but still under control. So what I require is the matrix of tilting parameters should respect the partial order on subsets. So we'll have to leverage this to prove a matrix tilted span theorem akin to tilted span theorem. So finally, we have got a one-shot simultaneous decoder for the Mac. So how does it work out? So remember, this is the original quantum multiple access channel. So we'll pretend that we're working with a perturb channel. So in the perturb channel, the senders first of all tensor in the ancilla independently, which they can do, and then they encode as before. So the tensor ancillas come here. Then the perturb channel C prime does not give the state tau as before. Remember, for Mn I got the state tau here, but here I'll get the state tau prime. Okay, so tau prime, remember, is the tilted state, tilted along a linear combination of M, N, and Mn, and plus these two ancillas are also hanging out here. Now the decoder will apply the single intersection projector pi hat Mn, but that brings case 0, case M, case Mn, case N, everything under control. So what do I get? I get a rate region not for C. For now, I get a rate region for the perturb channel C prime. The error parameters are worse, okay, not order epsilon to the 1/4 or something. But case M, N, and Mn behave as before with the good old mutual information quantity. Remember, they're calculated with respect to the original state, and I get this rate region, the simultaneous decoder. And once I've shown the rate region for C prime, I'll get the same rate region for C just by continuity. Error goes up slightly. This is because the tilted state tau prime is close to the original state tau. Okay, so this is basically the idea. So the question is, how deep does this idea go? Okay, so we took a running example of the Mac, but how deep does it go? So it turns out we can get a single intersection projector for a multipartite classical quantum system with classical condition. Okay. So here we had only one quantum system, but in general we can have several classical systems, several quantum systems. We can take tensor products of marginals. We can condition on a few of the classical registers. Okay, we can do all this, and we can still get a single intersection projector. So no fundamental new idea is required for this, but we just need to analyze matrix tilting along directions. So now remember, we had for matrix tilting we had to respect the subset structure when we analyze the MAC. But in the more general case, we need the lattice of so-called pseudo subpartitions of all the registers. Okay, so it's not just subsets; it's subpartitions. Not exactly subpartitions, something called pseudo subpartitions, which I define the paper. So if to really make it work, then the details are a bit hairy, but it turns out after some sweat they can be made to work. We can further construct the single intersection projector, and then we can follow it by the union method, the vanilla tilted span. So this gives a union of intersections projector. So this is required in inner bound proofs that do so-called non-unique decoding. So often in traditional inner bound proofs, when the receiver receives something, the receiver wants to find out what message was sent, and the receiver is not exactly interested in decoding the input string, but the receiver is satisfied in decoding the input string up to a certain set. So this is non-unique decoding. So this is applied, for example, in the Martin's inner bound for the broadcast channel, several other cases. It's also applied in Han-Kobayashi for the interference channel, so on and so forth. So it turns out they can be handled by the union of intersections projector. So this gives us a host of new results. So it gives us one-shot inner bounds for sending classical information through entanglement assisted as well as unassisted channels like the multiple access channel, Martin's inner bound with common message for broadcast channels. So this particular case was unknown earlier, even in the I.I.D case. Then we have Han Kobayashi and Chong Motani Garg L gamma inner bounds for the interference channel with and without shared entanglement. And this generalizes a whole host of results from the classical I.I.D setting to the quantum one-shot setting. Okay. So this is there in the second paper given on the first slide. Okay, so to conclude, what have we achieved? We have discovered powerful tools to handle unions and intersections in packing type arguments. So all these are channel coding arguments, the so-called packing type arguments. So they're useful for sending classical information through multi-terminal, assisted and unassisted quantum channels. So, but this leaves open some problems. How about unions and intersections for covering type arguments information? So covering type arguments arise in so-called source coding problems. And the big tool that we have in the quantum world for covering type problems is the complex split lemma of Anshu and Jain. Okay. So the question is, can we do covering unions intersections for covering type arguments for basically not the hypothesis testing relative entropy, but for the smooth max relative entropy. So this question relates to simultaneous smoothing also, and unfortunately our techniques don't quite work for covering type arguments. They don't quite give simultaneous smoothing. They do, I mean, say non-trivial things, but they don't seem to be strong enough for the applications. In particular, they do not give the natural rate region one would expect for the quantum Slepian wolf. Okay. And finally, one can ask, going back to packing type arguments, how about unions and intersections when the negative hypotheses are not of the form tensor product or marginals? So classically, we don't need that, but quantumly we need it. I mean, the smoothing, new idea number 2, smoothing needs that. Okay, that's all. Thank you for your attention.